Hello, this is Joseph Domingo, and here we have digital communications. In this part, we are going to be talking about efficient communication. Let's first talk about the various contributions made by mathematicians. First, we have Claude Shannon, in which he was born in 1916 and died in 2001. He was credited for the idea of using redundancy to add reliability to information. We also have Richard Hamming, in which he was born in 1915 and died in 1998. He was the first to implement error correcting codes and worked in research in the areas of coding theory, numerical methods, statistics, and digital filtering. Next, we have coding theory. It deals with error correcting codes for the reliable transmission of information across noisy channels. It is best demonstrated or represented through this diagram. Essentially, there will be a source sending out information. That information goes into an encoder, and then it goes through a noisy channel, and then gets decoded by a decoder, and then it will be sent out to the receiver. Now, source coding is where the message source is being changed into a code that is suitable for transmission through the channel. A source encoder is where the source gets transformed into a sequence of symbols or messages. Now let's talk about channel coding. Our first step is to encode the source. So jump is 0 and 0, step is 1 0, hop is 0 1, and glide is 1 and 1. Next we have the channel coding rule, which is x sub 1 and x sub 2. That will be turned into x sub 1, x sub 1, x sub 1, x sub 2, x sub 2, and x sub 2. We are going to be substituting these two numbers into those x sub values. First we have 0 and 0. Our x1 is going to be this first 0, and our x sub 2 will be this second 0, which means it's going to be 0, 0, 0, 0, 0, 0. Next we have 1, 0. Our x sub 1 will be the number 1, which means it's going to be 1, 1, 1. Our x sub 2 is 0, which means 0, 0, 0. Do that with everything else, and we can now get into the next part. Next, we have channel encoding. What we just encoded will correspond to the source. So jump is 0, 0, 0, 0, 0, 0. Step is 1, 1, 1, 0, 0, and so on. Now let's apply to a problem. Alice sent the message Y, but Bob received R equals 101,000. What we need to do is to find the nearest legitimate binary strings word. We need to find the binary string that is closest to 101,000. Looking at our options, it seems that 111,000 is the closest to 101,000, which would mean the word is step. This will mean that Alice intends to send the message step. Next we have the codes. A code word is a string of binary digits representing a message. So an example for this is our source is jump, hop, step, and glide. An encoded version of this will be 00011011. A code is the collection of all code words. So an example of this is 00000000011110000111111. Next, we have repetition codes. This is where we figure out how many are we going to put based on the given. In here, it says that given is r equals 4. This will mean in channel encoding, there will be 4x sub 1s and 4x sub 2s. You will then need to substitute accordingly. Next, we have error correction for repetition codes. We are going to be using a method called the majority decoding process. For each block of 5 binary digits, the original bit must be the one that appears most frequently in a block. In this case, if our received word is this, we're going to be finding what's the most frequent bit in every block. In this block, it is 0, in this we have 1, and in this we have 0. This will mean we're going to be converting them to 000001111 and 00000, making that our final answer. Next, we have parity codes. It is a binary word that has an even parity or equal number of ones. In here, we have 00000, which means it is even because there are 0 ones. In here, we have 00100. It is odd because there's only one 1. In here, we have 01100. This is even because there are two ones. Now let's have an example. We have 0001, 10, and 11. Our channel coding is x sub 1, x sub 2 to x sub 1, x sub 2, and y, provided that x sub 1 plus x sub 2 plus y is one of the same parity. Now we are going to be creating an even parity code. This means we will need to add a 0 or a 1 that when you add up all three, it will either be odd or even. We are trying to create an even parity code, so add a 0 or 1 accordingly. For example, in here, we have 0 and 0 and 0. If we add all of these, it's going to be 0, which is an even number. Same thing with here, 0 plus 1 equals to 2, which is a even number. So this will be our even parity code. If we are trying to create an odd parity code, it is essentially the same process. However, instead of finding an even number, we are trying to find an odd number. So in here, if we add all of this each, it will be an odd number. So 0 plus 1 equals 1, which is an odd number. In here, we have 1 plus 1, which is 3, which is an odd number. Do all of them, and we will now have our odd parity code. Next, we have Hamming codes. These are messages that take it the form of x sub 1, x sub 2, x sub 3, x sub 4. All messages have 4 binary digits where each code word is a length of 7. This means we will need to add 3 redundancy digits to form a code word. This will become x sub 1, x sub 2, x sub 3, x sub 4, x sub 5, x sub 6, x sub 7. Let's have an example. Notice that in the source I colored the numbers. This is because that each of these values corresponds to these x sub values. In channel encoding, you will see that x sub 5 is equals to 1, 2, 4, x sub 6 is equals to x sub 1, 3, 4, x sub 7 is equals to x sub 2, 3, 4. You will then need to substitute them to the corresponding values or in the source. So this means that x sub 1 plus 2 plus 4 is 1 plus 0 plus 0. Do that for everything and you will have our new code word. Next, we have the Hamming distance. It is the distance between two binary words of the same length. Let's have an example. Here we have x, y, and z with a binary word. If we are trying to find the Hamming distance between x and y, we'll need to align them both accordingly. Find what is different between the two, and that is a Hamming distance, which would mean our Hamming distance between x and y is 2. Next, we have the minimum distance of a code. It is the smallest distance between any two distinct code words in the code. Let's have an example. Find the minimum distance of this code. Step 1 is to find the Hamming distance of every single combination. Step 2 is to find the lowest Hamming distance between all of those combinations. In this case, it is 3. That means the minimum distance of this code is 3. Next, we have the detection and correction capabilities of a code. Let C be a set of code words and let 2e plus 1 be its minimum Hamming distance. This will mean the code can detect up to 2e errors and correct up to e errors. Let's have an example. How many errors can a code with a minimum distance of 10 detect and correct? Our minimum distance is 2e plus 1 equals 10. In order to get the error detection, we will need to minus the minimum distance to 1. That means 10 minus 1. So our answer is up to 2e equals 9. Next, we have the error correction, which is up to 4.5. In order to get this, we will need to divide the error detection by half, which means in this case, it is 9 divided by 2, which is 4.5. We will need to then round that down, which means we get 4. And that's it. Thank you for listening.